Okay. Seems to be. And there you go.
Thanks for that, guys. Okay, so this part of the series is just on a thing called variational message passing. It's the exact same optimization strategy that you've looked at over the last 2 sessions. But in this way, we do things in a more modularized form. So the first thing that we're going to look at is how we can extend standard variational inference, which is what you guys have looked at, into a message passing framework. And we're going to look at, start this off with a linear regression model. We'll then show that once you have these modularized formats, you can actually have very efficient extensions to more complex models such as semi-parametric regression and longitudinal data analysis. And finally, we're going to show how we address some non-conjugate Bayesian models, specifically logistic regression. So this is what we do in standard regression analysis. You just fit a least squares line to a set of data. But in a Bayesian approach, we just have to set up this hierarchy with some prior specifications over our parameters. So we have a Gaussian likelihood specification over our y's, the responses. We place a normal price specification over our regression parameters, the vector beta. Now we have this, so most people tend to use just an inverse gamma specification directly on their variance parameters. I tend to prefer to use this hierarchical price specification. This came from Andrew Gelman, where basically, oh, sorry, by the way, I'm using an inverse chi-squared specification. The specific kind of specification I'm using is just a reparameterization of the inverse gamma that you've been using in your previous talk so far. So don't think too much on that. But the reason why I use this hierarchical specification, the variance parameter, is that with this specification, it's equivalent to placing a half Cauchy prior over our standard deviation parameter. So it allows us to place arbitrarily uninformative priors over our standard deviation parameters. Now, you guys have gone through mean field assumptions so far, so I'm not going to go. I'm not going to go too far into that anymore. We're going to use the mean field assumption in this particular model that the vector of regression parameters beta and this parameter A that I've introduced into this hierarchy have posterior independence of the parameter sigma squared, where sigma squared is our variance on the residuals. So in the variational inference that we've covered so far, we replaced the true posterior density function by another density function Q. And we choose this one such that it minimizes the Kullback-Leibler divergence of, I forget the directionality, is it P from Q or Q from P? Does anyone remember that off the top of their head?
I think the way I remember is that when there's the 2 bars,
yep,
I read the 2 bars as from.
Okay, so it's the minimum Kullback-Leibler divergence of Q from P. That does sound right to me, actually. So
It checks out with what I done yesterday.
Ah, cool. I like that one, actually. That's a good one. The 2 bars are from. I like that. Okay. Now we have we assume that beta and A we group them together and give them posterior independence from the parameter sigma squared. Now it turns out when you go through some graph theoretical results, it turns out that you can make some extra independence assumptions. Basically, the beta and A will also be independent. This is to do with when you look at the directed acyclic graph for this representation, you'll find that the Markov blanket of the 2 parameters are separate. So you can assume that they're independent. Again, I don't want to go too much into that. Let's just take that for granted now. Oh, one thing, because we were having this discussion yesterday out in the coffee, out when we were having coffee, and we were talking about why we make particular assumptions for independence. So a couple of the guys were in that discussion, but so everyone hears this. Now I've assumed, as I said, that the variance parameter sigma squared is independent from the vector of coefficients beta. Now, the reason why we do this is we're actually using a concept called asymptotic independence from frequentist statistics. So if you have enough observations, you'll find that the Fisher information matrix will have a diagonal structure. And so we're using that concept and saying, if we have enough observations, if n's large enough, and we have uninformative priors over the parameters of the model, then we can assume that sigma squared, the variance parameter, will be independent of the coefficients. So these are the kinds of choices that we make for variational inference.
Daniela's asking, is the conditioning on y remains? Maybe.
Yeah. It's clear now. Sorry, there was something else I hadn't understood. Sorry, forget it.
No worries.
So now we're down to this. So the optimization problem has the following solution. We've gone through this a couple of times so far. So the optimal posterior density function for the parameter beta will have this form here, where you take an expectation that doesn't involve the Q beta distribution. You place that expectation over the full conditional distribution of the entire Bayesian model. And these are the computations that go into that. So in the first line there, you can see that, in the computation for Q star beta, you can see that we factorize the log of the joint distribution into the likelihood multiplied by the prior on the beta parameters. And you might say, well, what happens to all the other probability density functions? Well, they go into our constant. That's why C1 changed to C2. Does everyone understand that? Yep.
And you change too quickly. I need to. That's the joint. Okay, and then join, and then okay, conditional on everything. Okay. Gotcha.
Yep. And this goes into it in a bit more detail. So the first line is just basic logarithms. You notice that we don't apply the expectation to the log of the prior specification. Is that obvious to people, or not so obvious that we wouldn't?
You repeat the question?
So in the first equality there, we haven't placed the expectation over the logarithm of the price specification. Is that obvious, or would you like me to explain that?
Can you
explain?
Yeah.
Well, because it doesn't involve the density for beta, and the prior only depends on beta. So,
Oh, because it's minus Q.
Yeah.
Okay.
Yeah, minus Q. So it's not going to, yes. Sorry, just to be clear, guys, that's a minus Q here, meaning that there's no beta involved in that. And then you can go through standard expectations and vector algebra, and you'll find that this form here is the logarithm of a Gaussian density function. So I think we went through this yesterday and a bit today, so probably stuff that we're familiar with now. So Q star beta is going to be a normal density function, and you'll be able to extract the mean vector and the covariance matrix from the form of this derivation. I see some nods and some confused faces. Are there any questions so far? Okay. And similar arguments can be used to show that sigma squared and A will have inverse chi-squared Q density functions. Here are the parameters that you would get if you went through the derivations for under this standard variational inference approach. Here are the parameters for Q sigma squared and for QA. So if you just go through and work out all those things like you were doing in the seminar yesterday, you would get these results. And the form of the algorithm so far is that you just initialize. So first thing is you just initialize all these parameters. So sigma q beta, nu q beta, lambda q sigma squared, and lambda qa. You would just initialize them with certain values. You know, with some restrictions, obviously, you want to make sure the covariance matrix is positive definite. So you might just make it an indicator matrix just to start off with.
I missed what was lambda. Sorry.
Lambda q sigma squared is the, I think it's the shape parameter is the second parameter.
Oh, yeah.
Yeah.
Okay. The shape parameter of the
Inverse chi squared. For q sigma
so
squared.
first you derive Q of A, the family through the mean field approximation. And then lambda QA turns out to be the scale parameter of that.
Yes. Yeah. So the bottom one there, if you go through the derivations, you'll find that Q star A is the inverse chi squared with parameters 2 into lambda QA, where lambda QA is this parameter here. So yeah, you're right. First, you go through the derivations and then you extract those parameters. I'm skipping over a lot of the stuff we did yesterday because I kind of want to get into the message passing. But if you guys want to go over this, I'm happy to go over these parts as well. Okay. So this is the form of the algorithm. So you initialize all those parameters, which is essentially initializing all your posterior density functions. And then you cycle through the algorithm by updating the parameters for A, then for sigma squared, then for beta. It can be in any particular order. I'm just choosing it here. And you just continue that cycle until you have convergence of the Kullback-Leibler divergence. Obviously, as we were talking about yesterday, we don't look specifically at the Kullback-Leibler divergence. We look at the elbow. I'm not going to go into that today either because I think that was covered quite well yesterday. Okay, so the reason why people generally use variational inference is because it's faster than MCMC. Like, that's one of the things we look at. It can often be a trade-off between computational efficiency and accuracy. We try to reduce the drop-off in accuracy as much as possible, but that's the main purpose why we like to look at variational inference. It's a nice, cheap alternative. But for basing inference on more complex models, we have to redo all the derivations. I don't know about you, but I hate deriving stuff. It's time consuming. When you give a presentation, right, you don't start every presentation from scratch. You use bits and pieces from previous presentations. You use the layout from that previous presentation to construct your next presentation. So in variational inference, we don't seem to do that. We just rederive everything from scratch again. So when we're designing these algorithms, we're telling you that the computations are faster and that it's true, but the actual working time required for it, in some cases, can actually be longer than, just getting some sort of sampling algorithm such as InSTAN or something like that to do the problem for you. So considering all those things together, variational inference really isn't always a faster alternative. So for instance, if we wanted to extend our regression model to this Gaussian response linear mixed model, we'd have to go through all of those derivations again. We'd have to work out the updates for these beta parameters, for these U's, for these sigma squareds again. There's a covariance matrix for the random effects. All those things you would have to redo again.
Not exactly, because the distribution of A conditional to others on depend on sigma square, if I'm not wrong, right? You don't have to do it again because if you calculate the updates for the A, for instance, and you only use the sigma square process, or use other as well.
Sorry, I didn't understand the question.
Yeah, so I mean that if you want to redo derivation for this, then for some variables you can still reuse what you have done before. For instance, if you try to update A,
yep,
then other things only depend on sigma square. That's very Yes, and so there is no U sigma, big sigma and A in the conditional distribution of A.
Yep.
So I think you guys can reuse some elements from the previous.
There are some ways in which you can extend it. So you're right, I am exaggerating a bit here, but I think so I think these two would be the only ones that you would be able to actually reuse again. You would definitely have to re-update these guys. This is a new thing entirely. This is going to be different because of the implications of this parameter here. So you're right, I am exaggerating here, but it is going to, the point is it is going to be a tricky task, you know, not necessarily tricky, it's just going to be a very tedious task. And I guess what I'm trying to get at is we don't want to work hard, we want to work smart here. We want to find a way to, like, if we really want variational inference to be a strong alternative to MCMC, we have to come up with something that's a bit more efficient, not just in terms of computations, but in terms of the time that you have to put into work, into working out these things. But yeah, good point. Thank you. Thank you for clarifying that. So this is where variational message passing can help make our lives a bit easier as people in variational inference. So this is Matt Wand. I did my PhD with him, and he wrote up a big article about this a few years ago. And when I talk to people about variational message passing, one thing they usually ask is, has there been like some sort of workshop on it or something like that? I don't want to say there hasn't, I just don't know if there has been. So I guess this is a good chance for us to go into this into a bit more detail, especially because when I talk about variational message passing and you only have like half an hour to discuss this kind of work, it can be hard to get the point across. Okay, so let's go back to our Bayesian linear regression model. We've seen all this before. Okay, so as I said, we saw this in logarithmic form before. We had this update here. Now we've just turned it into an exponential and have normalization constant out the front. So that's the posterior, the Q density function for the beta parameters. If you expand this out, if you expand that quadratic form out, you can actually factorize this density function with the second line here. And if you look closely enough, you'll see that the first
sorry, can I ask, can you can you indicate with a cursor or something which formula you're looking at?
Yeah, sorry about that.
No, thank you. Thank you.
So what I was saying was that you have, unfortunately we can't highlight, but in the first line here, that was the Q density function for the beta parameters that we worked out through our variational inference approach. And what I was saying was that if you look at this quadratic form here, you can expand it out, and what you will find is that the Q density function can factorize into this form here, given in the second line. And if you look at that closely enough, you'll notice that the first factor is a contribution that's completely from the likelihood. So how do I know that? Well, it has a contribution from the variance parameter there, the Q expectation of 1 on sigma squared. It has contributions from the design matrix X, and it has contributions from the observations themselves, the vector of Y's. And the second component is completely from the prior specification, where that variance component is the variance that we placed on over the price of the beta parameters. And this shouldn't really come as too much of a surprise, because this is what you do in standard Bayesian inference, right? You have your likelihood specification, you multiply it by your prior, and you do some marginalization over that. So really that's not too surprising, but what it entails is it means that you can take advantage of this factorization here. So instead of working with a directed acyclic graph as we had in the previous variational inference approach, we now work with this thing called a factor graph. So in a factor graph, you'll see a bunch of square nodes. Now, each square node represents one of the probabilistic specifications of our model. And and we call them factors. And each of those factors are connected to all of the parameters that contribute to that probabilistic specification. So obviously the price specification on beta only depends on beta. And a factor connected with its neighboring parameters is what we call a fragment. And a fragment is key to building up the complexity of our model and modularizing the computations that are required here. So bear with me a bit on this because it can be a bit tedious, but you'll see that as we start to build up simpler and simpler models, extending them to more complex models can become much more efficient. So we have a fragment representing our likelihood specification. We have our fragment representing, we call this like an iterated inverse chi-square density function where you have a chi-square parameter that's conditionally dependent on another inverse chi-squared parameter. And then you have a price specification for the inverse chi-squared prior there. So that should seem reasonable for everyone so far. And so we showed that our Q density function for beta can factorize into this form. And so what we're going to do is we're going to change our updates that we had in the standard variational inference algorithm where you keep updating the parameters. Instead, we're going to talk about messages passed from factors to parameters. So we literally just for now, let's just define the message that's passed from the likelihood specification to the vector of beta parameters by the first factor here. And let's define the message passed from the price specification to the parameter beta by the second component there.
Sorry, what was a factor again?
A factor is the square node.
It's a square node.
And each factor represents one of the probabilistic specifications.
And they circle out the messages. No.
The circular nodes are just the parameters, and the message, you can think of the messages as being passed along the edges.
Okay.
And so the directed acyclic graphical representation that we had in the standard variational inference algorithm, it just doesn't support this kind of modeling. So we require this factor graph representation. Any questions on that so far? Or is anyone confused by it?
No, can I ask you a question? Sorry. The graph that you are, no, it's not graph, but that you have at the top, where you got where you got all these factors and these components or whatever. How do you build that? It's just a representation of the quantities, full stop. Yeah, there is no interpretation of relationships or anything, or am I wrong? Because I see graph actually represents the relationship between the variable, yeah? And I wonder whether this is a similar interpretation, perhaps not.
Yeah, well, we're building it up directly from our Bayesian model that we've got here. So you can see that there's as I said, I'll talk about a fragment as a factor connected with all of its parameters. So we've got a fragment here that's highlighted representing the price specification.
Yeah.
The likelihood specification and so on and so forth. So we build up the factor graph based on our Bayesian model.
Okay, thank you.
Yeah, so the Bayesian model defines the factor graph is one way of saying it.
Yeah, and there are little components which actually are related to particular bits of the model. Yeah, okay, thanks.
Okay, so we define these messages over here. So let's actually form like a way of actually defining and updating these messages. So if you have a factor and f, and it's going to send a message to one of its neighboring parameters theta, well, the message will be derived in this form here. So more specifically, if we want to look at the message from the likelihood factor to its neighboring parameter beta, it will have this form here. Does that look familiar to anyone? The form of it, at least. It should look very similar to what we had for the standard variational inference algorithm, except now, before you would have the full joint model here. Now you just have the likelihood specification here. So we're basically, the only difference in here is just that we're using the likelihood specification. So we're focusing our expectations and our updates solely on the particular probabilistic specification within the factor. That's the only difference in that update form so far. So we have messages from factors to parameters, and they have that form there. We also have messages from parameters to factors, and the fact that you have return messages from parameters to factors, that allows all the different building blocks, these different fragments, to communicate with one another. Because if they're all just sending messages to parameters, then you would get no communication between the different building blocks. So the message that a parameter passes on to its neighboring factor is simply the message that it received from another neighboring factor. Normally, it would be the product of all the messages that it received, but all the models that we're going to look at today have just designed it such that we'd have this kind of linear construction here, so we don't have to worry about making this even more confusing. So just remember that factors, they send messages given by that particular update in the second equation there. Parameters, they just send back, they just transmit those messages on. They receive a message and transmit it to its other neighboring factor.
Do the parameters also send back the same message that was received from that same factor?
No,
Right.
So
All except that one.
yeah, exactly. Yeah, yes, correct. Every other factor except that one. Yeah. What that factor will get is the messages that it received. Does that make sense? Yeah. So it turns out that the message, we'll go into this in a bit more detail soon, but it turns out that you can factorize the well, actually, let's look at this message here from the likelihood specification to the vector beta. You can summarize it if you go through the algebra into this form here. So you get the betas together, you put them into a vector, and you form the other vector accordingly. This really is the form of this, this here, where you have your parameters over here in a vector, and then just some other constants in another vector. That's basically, this particular form here is basically a multivariate normal density function in exponential family form, where this is your vector of sufficient statistics, and this is your natural parameter vector. Are people familiar with that kind of form? Yep. Likewise, the message to sigma squared, we haven't derived this yet, but it could be summarized into this way. And so this would be the vector of sufficient statistics for an inverse chi-square density function. And this would be the particular natural parameter vector. So think of the vector of sufficient statistics as defining the probability density function, the family of probability density functions, and this vector of sufficiency and the natural parameter vector then defines which particular density function it's going to be. So then, if that's truly the case, then by restricting the form of these messages to the exponential family form, we can completely characterize these messages by their natural parameter vectors. So if we know the vector of sufficient statistics for a message, the density function then would be completely defined by this natural parameter vector here. So really what we're going to do when I show you the code is you'll see that all the code has been sorted into natural parameter vectors rather than messages. And that's good because we don't want to work on the exponential scale. We can work on the log scale here where things, where we won't have all these kinds of errors carrying around. So just a bit of stuff about a Gaussian density function in exponential family form. That's what it looks like. And you can see that there are these one-to-one relationships between our vectors of natural parameters and our common parameters, the covariance matrix and the mean vector. That's all this page really says for now. Likewise for the inverse chi-square density function.
Sorry, can you go back one slide?
Sure.
I realized I missed a bit. The VEC function.
Oh, sorry.
Exactly.
Sorry, yeah, good point. Yeah, I should have actually told you that. When you have a matrix, the VEC function literally just gets the columns of those matrices of that matrix and just forms a vector out of those columns. Concatenates the columns from left to right.
Okay, take the columns, put them in a vector. Okay, and vector to the -1, I guess.
Oh, sorry. Yeah, good point. That's the inverse of that parameterization. So suppose
Same object or so, like, yeah, something you constructed.
something that was,
And you know
yes.
how big columns were.
Yeah, so it transforms it back. Yeah, but yes, probably I think it would be better to put something like d by d at the bottom here to specify that it's going to, yeah.
It's okay, it's okay.
And this is what we have for the inverse chi-square density function. We'll have a chance to look at that as we go through the derivations. So what I want to point out here is that once you've stored up the messages passed within these fragments, then that can be applied to any model that has that particular probabilistic specification. So for instance, the price specification, the Gaussian price specification, that was developed in 2017. The Gaussian likelihood specification was developed in that same publication. The iterated inverse chi-squared fragment that was developed by Maestrini and Wand a couple of years ago, and likewise with the inverse chi-squared price specification. So the code that was developed in those models, I've used directly into this linear regression model. So I actually haven't done any work here. I just used the code that they had and built up my program around the coding that they implemented. So, oh, and eventually we're going to have to get to Q density functions. In a little while, I'm just going to go through on the board and actually derive some of those messages. But for now, let's just see how this translates to variational inference, where we want to actually determine these Q density functions. So remember how we factorized the Q density function for beta? We had that message from the likelihood specification and the message from the price specification that were factors. We factorized it into that form. So it turns out then that the Q density function for each parameter is just going to be the product of all the messages that it receives. So the Q density function for beta would consist of the message that it received from the likelihood multiplied by the message that it received from the price specification. We went through that earlier when we were factorizing these things. But remember how I said we're going to keep this in exponential family form. The good thing about the exponential family form is closure under multiplication. So it turns out that when you're working out the natural parameter vector for the Q density function, it would just be the sum of these component-wise natural parameter vectors. And that's what we have in the second line there. So that's just a nice result that comes across because we're restricting things to the exponential family. Okay, so none of this really makes sense until you actually start deriving a few things. So I'm actually, I didn't have time to put all this up in slides, but I'm better at doing this on the board. So let's just go ahead and derive one or two of these fragments to really understand the computations that we're doing here. So if I can bring this around. Yeah. Okay.
I think so. I think so.
Yeah, I mean,
It's right to the center.
Is there any way we can zoom in?
I have no idea.
I'm not sure.
Putting that yesterday. I think there is a way.
you can't get very zoomed.
Oh.
Yeah.
I mean, or I could like turn on the camera on my laptop and put it.
Probably the easiest option.
The easiest thing to do, all right. Right, let's do this low-tech solutions.
You need to act or rear camera, front camera.
So front meaning by
You'll see the audio.
maybe if the chat.
We can get closer.
It's just inverted.
Myself.
Right, okay.
Oh, wait, but my camera is really.
It's exactly like the one.
Let's use someone else.
Let's see if it works like
It's.
Maybe because it's.
No, look at that, guys. I think we managed. You now have to stop sharing though.
Oh,
Well, they managed.
oh, that's not so bad. Oh, that's great.
Yeah.
does that work?
Stop sharing the screen so they see you big.
Right big.
You can also just pin it. Shall I pin it? Or is it already pinned?
Does that pin it for everyone or just for you?
No, it pins it for everyone. No, I think it's already pinned. Oh, no, maybe it does pin it just for me.
Do other people see correctly? Yeah.
If it try and write, I don't know if it's.
Yeah, I think it's okay now.
Also, the recording is.
Yeah.
Yeah, it should be left to right.
That was ages ago, yeah.
No.
It's fine for everyone else.
It's fine for everyone else?
Okay. On there, but it's fine.
Okay. So look up here, not on there for you guys though. Okay, so
No.
Oh, there is a way. I mean, I can do it if you want. Like you just go into Zoom settings
Oh, what? Sorry.
to mirror this one, basically. There's a way to do it.
I mean, probably fine.
Yeah.
Oh.
Spent too long in Zoom settings, so.
I mean, this is clear enough.
Yeah, we were seeing it the other way around from the room.
Ah, okay.
okay, so
Can I ask a stupid question?
go ahead.
Okay, before you derive this, which probably will clarify things, is
Yep.
why is this so interesting, powerful, and convenient compared to the graphical models?
Yeah, so keep in mind that this is entirely based on a graphical model as well. It's just a different graphical construction.
Yeah.
The reason why it's convenient is that, for instance, with this model here, I haven't actually done any work to develop it. When I coded it up, I just used the coding that was available from previous publications. So once you've coded up your message passing updates, they can be used in any other model that uses the exact same kind of probabilistic specification.
Okay.
Very simple stuff here with the Gaussian prior. I'm going to show you how you derive those updates. And once you code them up, you can use them in any model that uses a Gaussian prior specification.
Okay.
It's about modularity, essentially, breaking the model.
Modularity, yeah.
Okay.
And that's what I was saying at the start. This makes it a decent alternative to MCMC in the sense that now you don't actually have to keep rederiving things. So we showed that the message passed from a factor to a neighboring parameter, which is a function of that parameter, is going to be the exponential of the Q expectation of the logarithm of that factor. Okay, so we saw this before. So first, let's work out this expectation here. So log of P of beta, which is defined here, is equal to -1 or 2 sigma beta squared, beta transpose beta, plus some constant terms there. Now, if you apply that Q expectation here, what happens if you apply this particular Q expectation? Nothing. So we can do this. This one's pretty cheap. We can apply that directly because according to this density function, according to this expectation here, everything's constant. Now, this is equal to, because we have this quadratic form here, we know it's going to be Gaussian, right? You can factorize this as this. Does that make sense? Is everyone familiar with that? So I've applied a trace to this. I can do that for free because it's a scalar. And I can put an indicator matrix in for free. And then I can rotate the order of these things around.
You don't need to then divide by like n or something where n is the dimension of the. Is it not going to put beta transpose on every element of the diagonal and then?
That would be a different operation.
Oh, you mean something else?
He's just multiplying by the identity.
Yeah.
So it's not a matrix. Wait, no, I'm confused.
Identity matrix. It's an identity matrix.
So you don't have a diagonal matrix where beta transposes every element on the diagonal.
Beta transpose is a matrix.
Oh, right, I see. Okay, yeah, I got it.
And then another bit of cheap matrix algebra is this. So turns out that trace is a special form of an inner product where you just where it just basically gets applied. You can basically separate the component vectors, the component matrices, and vectorize them. That's just a nice bit of cheap algebra, matrix algebra that we can use. And then this has the form . And this is basically the logarithm of the Gaussian density function in exponential family form. So if that's the logarithm of our message, what then would be the natural parameter vector for our message?
Second square bracket.
Yeah, the vector on the right. So that's how we define that's how we work out our messages, solely by recognizing the vector of sufficient statistics and then working out the natural parameter vector. So I think we have a bit of time now. So that's how we work out this natural parameter vector here, simply through.
Share screen again.
Oh, sorry. Where do we go to share screen?
Escape.
Zoom settings.
Yeah, and then you need to go into Zoom. Yeah, then just share. Yeah. Oh no.
No. So to give you guys a flavor for how it works, what I'll try and get you guys to do is work out not so much for the one for this guy here, but the natural parameter vector update passed from the likelihood specification to beta. Do you guys need a reminder? I can write that on the board here. See a stripe before? Yeah.
Maybe on the eraser or something. Sorry, straight on the eraser, maybe.
Oh, yeah.
I'm not
Actually, you probably would have.
Oh, looks so great. The message. So what we worked out was the message from the prior, right? Now we
Yes,
have to work out the message from the likelihood, yes?
from the likelihood. Got any paper towels just to try this?
There's probably some.
There is fence there at the other.
I'll see in the teaching.
See.
It's still going to be an expectation with respect to minus Q beta.
Yes, yeah. Whenever you're working out the message passed to a parameter, it's always the expectation without that parameter.
Okay.
So that's what you want to start.
Like minus a half. Sigma squared.
Oh, yeah.
I mean, are we doing that together? Yeah. What?
So just as a function of beta, this would be
Yeah,
so
Let's try some of these.
it's just wet. Oh,
oh, can you not see?
Faded,
Yeah.
yeah, it's fading a bit. I don't know if any of these. Even
That
worse.
feels better. Oh,
Yes,
that's
maybe
much
the black
better,
one.
much better. Not here.
It's not that. Well, but you have sigma. Huh?
No, but it's fixed in this case, right?
okay.
Sorry, that shouldn't be a beta, that's sigma squared.
Okay.
Just as a function.
So the Y's, you forget about them.
Yes. If they're on their own.
Yeah.
I thought you were working out the message passed only to B. Not also to
Then I get confused with the back function.
Yeah, which is why we can.
Yeah, I guess, a quick rule here is the trace of A and, sorry, B is equal to vec A transpose vec B.
Basically like a generalization of the Frobenius norm, right? Because if you were
Correct.
to B equals to A.
Yes,
then you
yeah,
have the Frobenius norm on both sides.
correct. Well, it's the inner product from the,
Yeah, it's the inner product of
it's the
the-
inner product that defines the Frobenius norm.
That is a scalar, then you
Yeah.
can add the trace and then you can break it up that way. External.
So that's where I got here. Yeah, so I use the trace, so I using the trace on this, pull beta around here. Yeah,
So we're taking an expectation with respect to anything that is not beta. Yeah. And we're considering this only as a function of beta at the end of the day anyway, right? And so because beta doesn't appear anywhere here in the distribution.
Yeah, you can just ignore it. Okay.
so you're asking about where you apply the expectation. Were you asking about where you applied the expectation?
Yeah,
Yeah, so this is that part there, right? Now we just have to apply that expectation to this. So where do you think it's going to affect things?
On the natural parameter.
Yeah, on the natural parameter vector. So you just have to apply that expectation to the natural parameter vector. And the only parameters that it's going to affect are the one on sigma squared. So you get these, so you literally get, you'll see it literally gives you that update we have on the bottom left.
Okay,
Yeah.
okay.
So
Sorry, sorry, what did you say about the expected value?
No, I guess I just got confused as to what would actually.
what would actually be affected?
Yeah.
Just remember, obviously, things like X's and Y's, that's just data, so that's not going to get affected by Q expectation. But parameters which do have, which obviously have Q density functions like the sigma squareds, they're going to be affected.
That's pretty much it, isn't it? Because beta.
That's it.
Yeah, okay.
Yeah, beta, yeah, because we're taking the expectation without beta.
And I guess we're working under the assumption that under the Q density beta and sigma are independent, right?
Independent, correct. So that allows us to separate them like that. Yeah. Sorry, I should have mentioned that. That's a good point. Yeah, the reason why that's working is because of the assumption that beta and sigma are independent. So yeah, once you apply that expectation, you'll literally get a natural parameter vector with this form here. I'll avoid doing it for the sigma square parameter. I guess we all get the idea of how this works now. So we do that for the likelihood specification for both messages. We do that for this specific, the iterated inverse chi-squared specification for both parameters, sigma squared and A. And we do that for the price specification on the inverse squared parameter. So I'm just curious, based on all that, what do you like on this linear regression model? What do you think would have been more time consuming, this, and be honest, this one or the traditional variational inference approach? Definitely this one, like definitely this one. This took a lot of time, right? To put all this together. Like you've got to work out, what 1, 2, 3, 4, 5, 6 messages. Whereas in variational inference, you would have just have to work out 3 posterior density functions. So you might be thinking at this point, then what's the point of this? So this is, by the way, this is just the general algorithm that you would use. You just initialize messages from stochastic nodes and parameters. Think of them as the same thing, because they are. And then we update our messages from factors to parameters. We just go through a cycle where we update all these messages, and then we monitor the elbow in practice for convergence of that. But yeah, so at this point, this seems like a very inefficient way of doing variational inference. I mean, the amount of work we had to do just to get one message up there, was quite tedious. But you'll see that what we can do now is build some seriously good model complexity based on these structures that we've already defined. Should you guys be up for a break now? Quick coffee break? Yeah. Yeah.
10 minutes?
Basically, what you do.
Yes, I mean at 2:10. I think the timing's good. Yeah.
Perfect.
For each family of history, etc. Figuring out message. Maybe we should, and then when you have
Pause the recording or something?
Oh, yeah, good idea.
algorithm will run like God found is to give it what distributions you have, take those messages.
Recording resumed.
Okay, so as I was saying, when we were looking at the Bayesian linear regression model and building up that problem, it's actually that took a lot of time just to build up that problem. And I could see a few relief faces in the audience here when I said, yeah, you know what, I'll skip over some of the other messages. I completely get you on that, don't worry. But so on face value, when you're just looking at a Bayesian linear regression model, you might just say, well, wouldn't it be easier just to do the standard derivations that you'd normally have. And yeah, it would be, but you're limiting yourself to Bayesian linear regression. So let's build up a bit of model complexity and look at things such as non-linear data sets where you would have to look at semi-parametric regression. So for instance, just in this data set here, we have fuel efficiency. Sorry, it's cut off part of my title there, but you have fuel efficiency as a function of the weight of the car. And we're going to address this non-linear data set with semi-parametric regression. So you have a matrix of fixed effects and a matrix of random effects, which constructed by a set of spline coefficients evaluated over your design points. Is everyone familiar to some extent with non-parametric or semi-parametric regression? Okay, great. So the way we model, the standard approach for modeling semi-parametric regression, actually, I don't know if it's the standard model for using it, but it's a model that I really like, is to set it as a linear mixed model. So we use mixed model-based penalized splines. I tend to use O'Sullivan penalized splines, but I think any sort of B-spline can fit into this this kind of modeling. So you have your fixed effects parameters and your random effects parameters. Your random effects are represented by the coefficients U, and your fixed effects by the coefficients beta. So here's the Bayesian semi-parametric regression model. We have a Gaussian likelihood, that should be beta and U, sorry, conditional on beta and U. So we have a Gaussian likelihood specification over the responses, Gaussian priors over the score, Gaussian prior over the fixed effects. We have this Gaussian penalization specification over the random effects. So the variance parameter here captures our penalization. And then we have these inverse chi-squared density functions that we looked at before, and these inverse chi-squared prior specifications that we looked at before. Any questions on the model itself? Okay, so let's build up our factor graph for this model. So we have the likelihood specification. What's the difference between this likelihood specification and the one that we had for the linear regression model? In terms of the probabilistic specification though, what's the difference?
It's in the graph.
For this guy here, what's the difference between this and the likelihood specification that we had?
It's not anymore one more
We've got U.
argument.
Yeah, I would say there's no difference.
Okay.
Oh, because U is also Gaussian together.
Yeah, because U and beta are together. It's just one vector.
Two other things.
Yeah. Like when we develop the code for these guys, we don't put a limit on. We don't say the beta has to be of length 2. So I'm saying that this fragment here is exactly the same as what we derived for the linear regression model.
And the capital Z also like observed and fixed.
Yes, sorry, capital Z is your matrix of
Sorry,
yeah. Yeah, so just to be clear on this, guys, we're going to carry these X's and Z's around with us. Yeah, so basically everything that we did to derive these updates here are going to carry over directly into this semi-parametric regression model. So we don't have to do any work there. We just need to copy and paste our code when we're coding this up.
So basically the only difference is that so assuming we're thinking in terms of the first model, our beta vector will just be longer. Is that the only difference?
That's it.
Okay.
Yeah, got a longer beta vector. So obviously when you code it up, you got to be smart. You don't just say, we'll limit beta to 2 vectors. So you just be a bit, thoughtful about it. Then we have this fragment here, which represents the penalization structure that we have So we have our fixed effects and our penalization over our random effects. Does that one look familiar to you? Based on what we did in the previous model.
I feel like this is bigger because it depends on two things rather than one.
Yeah, you're right. This is different. This is something we haven't actually looked at yet because you have a vector with fixed effects and a vector with random effects.
Yes.
Yeah. So yeah, correct. This one's different to what we had before. We have these iterated inverse chi-squared specifications. We derived that for the previous model so that the code can literally be recycled.
So that's exactly the same as the previous model.
Yeah.
This is, I mean, it's just different labels, but it's
Different labels, but in terms of probabilistic specifications,
okay.
same thing. And same with these, sorry. This is a bit from an old talker. You've got, I'm talking about them as inverse Wishards. An inverse Wishard is just a matrix extension of the inverse chi-squared. So ignore that. Wherever you see Wishard, think of it as chi-squared. But yeah, these prior specifications over our inverse chi-squared parameters, they were just developed in that simpler model as well. So once again, we're just, we're just recycling derivations here, derivations, codes, and things like that. They all get recycled into this new model. The only thing we have to work out here is the Gaussian penalization fragment. That's the only new bit of code, new updates that we have to work out.
So the second sigma, the sigma beta here, where does that come in now?
The second sigma. Sorry, where are you?
So in the so you have the scale for the fixed effects and the scale for the random effects. And sigma u is the scale for the random effects, right?
Yes.
So where is the sigma over the betas now?
That's a hyperparameter.
So it's not given
So because beta is our fixed effects parameters and u is our random effects parameters.
but in the okay. But didn't we in the previous
Slide, let's have a look.
maybe I'm okay. I think I have to check.
Think of it as a linear mixed model. That's the important thing. Like when you're addressing this, don't think of a spline so much as you're thinking of a linear mixed model. You've got your fixed effects parameters and your random effects parameters like you would have in any standard linear mixed model.
No, sorry. Yeah.
Got it? Yeah, perfect. So yeah, the only thing we have to do now is this one fragment, the Gaussian penalization fragment. And this is the updates that, if you went through all this stuff again. So basically it's saying that for any probabilistic specification that has this form here, you just use these inputs. So you always input your Q density function because you're always initializing them. And then you run through these updates and you'll get these natural parameter vector updates for beta and u together and sigma u squared, the penalization parameter.
Oh, so it's from, okay.
Are there any questions on that? I'm assuming people don't want to go through the derivation again. But any questions about how we implement this or?
And so we do know, like in closed form, for example, what the second moments of u under q and all that stuff.
This thing here?
Yeah, for example.
Yes, yeah. Because you use your natural parameter vectors
Okay.
to determine these covariance matrices, these expectations. And so once you've worked those out, then you plug this in here. Yeah. Yeah, so these expectations are first determined, and then you can define your natural parameter vectors. So that's all we have to do then to extend it to a semi-parametric regression model. We just have to determine that fragment, and then you run through the standard variational message passing algorithm. So although it seemed like we had to do a lot of work to set up the linear regression model, and you're right, we did, but now to actually set up a more complex model, we just have to do, develop one small fragment.
Basically, in this framework, someone who develops a model and they use message passing to sort of question, they just have to give you, well, the equations for the model, and then the equations for the messages,
Yes.
and then the code,
And the code.
you need to
Yeah.
copy-paste the code. Okay.
Yeah, I mean, all the code you're going to see, that's literally, all that code came from someone else. Like I didn't develop any of the code that we're actually going to, actually there was one thing, but we'll go into that later. But yeah, you just take the code from other places and recycle it. So yeah, you can get these kinds of fits data. Like, I mean, we're not really worried about the fits. What the point I'm really trying to get across here is the efficiency with which you can do things here. So let's have a look at a multi-level data model and see what extensions we'd need here. So suppose we have M groups. Let's try and put this into something. So, okay, we have 21 towns and 25 people in each of those towns. So M is going to be 21 and each NI is going to be 25. You have your X's and your Y's that have this hierarchical structure. And this is the Gaussian response linear mixed model that you would use. So once again, you have your fixed effects and your random effects. Your random effects have this form here, where now you have this covariance matrix as opposed to a simpler sort of diagonal matrix that we were using for semi-parametric regression. But apart from that, it's the same concept of linear mixed modeling that we were using for semi-parametric regression. And just defining these matrices here. Okay, so we're all convinced that this is still the same likelihood specification. Cool. Now, the Gaussian, this kind of specification can be a bit, it can be a bit more difficult to work with because of this covariance matrix structure that we've got here. Before, we just had like a scalar parameter placed along a diagonal of a matrix. I'm actually not going to go into this covariance matrix, into the inverse Wishart distribution today, because that's a whole other headache that we don't want to worry about. So let's assume that what we did for the semi-parametric regression model can be generalized to this kind of modeling here, where we have a covariance matrix as opposed to a variance parameter. Let's just take that for granted. It turns out that, you can generalize it to that setting, but I don't want to go into it because it can be quite tricky. So basically, this fragment here is literally the fragment that we saw with the semi-parametric regression model, just extended to accommodate a covariance matrix structure. Same with these, I'm going to apply the same thing for these iterated inverse chi-squared fragments. Let's assume that they can be generalized to an inverse Wishart, as well as the prior specifications as well. So after going through all that, is there anything then, like assuming that we understand that these inverse chi-squared specifications and these variance specifications can be extended to Wishart distributions, is there anything new that we're seeing in this model? Yep, no, yep, correct. There's nothing new in this model. So basically, all the code that we developed in from the linear regression model and that extra bit of code we developed for the semi-parametric regression model, that gets applied immediately to this model here. So there's nothing new that we have to do for this model here. I don't don't want to waste too much time going over some background information, but I'm assuming everyone here has worked quite a bit with linear mixed models, multi-level models, things like that. Okay, maybe it's worth going into this then. So it turns out that the covariance matrix can be a tricky thing to work with. The covariance, so new here is just our vector of fixed and random effects. It turns out that when you determine the covariance matrix, it can actually be quite a tricky thing to determine, as well as determining your posterior estimates for the residual variance. It's to do with the matrix A. So it turns out that the covariance matrix for the parameter nu is simply the inverse of this matrix A, which has a particular form. And the mean vector has a similar form that depends on the inverse of this covariance matrix. So what's the problem with A? So consider our fictitious setting where we had 21 towns and 25 people in each town. The covariance matrix would have this structure where the blue spaces represent parts of the matrix that are zero, and the colored spaces represent parts of the matrix that have no zero restrictions on them. So that's what the matrix would look like. But suppose instead of like 21 towns, sorry, I'm gonna move this. If we had 1,000 towns, it would look like that. So a terribly sparse matrix that you would have to invert. And that's a huge matrix to invert. It doesn't always, sometimes it causes your software to crash. So we want to somehow take advantage of the sparsity of this matrix. And so we can do this with some, just some algebraic tricks. I don't really want to get lost in the details here. All I'm saying is that with the code that I've set up to the GitHub repository, it's using these streamlined computations. So basically, we don't have to worry about inverting this large sparse matrix. We take advantage of the fact that there are these, very sparse components here, and we work solely with these smaller A matrices like A11, A121, A221. It makes the computations feasible. But it doesn't really have anything to do with message passing itself, so I don't really want to get lost in the details here. But I've left this presentation on here so you can read into this if you are interested. So I think it would be best to skip through that because I feel like we'd lose the main point of this talk, which is really how we construct message passing algorithms. But yeah, like as you guys worked out, there really is no difference in the fragments that we're using in this linear mixed model here. It's exactly the same as what we had in the semi-parametric regression model. So what we developed in the semi-parametric regression model gets carried directly over to this linear mixed model over here. And I think to finish off the talk before we look at some of the code that I've posted up, I'd like to just talk a bit about non-conjugate models. Has anyone touched, I don't think we touched on non-conjugate models yesterday. I think we only looked at, I think everything was conjugate yesterday. Was it the same this morning as well?
I think so, true. Like one of the examples was logistic regression. So.
Logistic regression? Oh, what did you use? I wish I was here.
The black box BI.
Black box BI.
Second one, but
Yeah.
at least he was talking about black box BI.
Okay. I'm going to look at logistic regression as well. So suppose you have some binary response data. So the blue curve represents the probability function that generates the data. And what we want to do is, allow our variational message passing models to be able to handle this kind of non-conjugacy. So let's just look at a simple Bayesian logistic regression model. We have a logistic Bernoulli specification over the responses, and we tend to place Gaussian priors over the regression coefficients. So this is the fragment, the factor graph for the model. You have a fragment for the price specification. Obviously, as we've gone over a lot, we've seen this before, but we have this logistic likelihood fragment, which is going to be different. And when you go through and derive the messages for this, the message that's passed on to the vector beta, it has this form at the bottom here. When you go through the things that we did before, you'll get this form here. But the problem is this expectation here. It doesn't have a closed form solution. And the messages that are typically passed to beta from other fragments are within the Gaussian density function. So what we're going to attempt here is to enforce some kind of conjugacy, force this message to have a Gaussian form. So that will entail some sort of approximation that's required to get that kind of conjugacy passing through. So I've cited a paper here, 2014, and in that paper they showed that you could use a fixed point iterative scheme based on derivatives and second order derivatives to determine the mean vector and the covariance matrix in for a Gaussian parameter in variational inference. Again, I don't want to get caught up in the details here, but it turns out when you use those updates, you get the following form for the natural parameter vector over here. We still haven't done anything. We're still using the same approach. We're still stuck with the same message that we had on the previous page. We're just representing it in a new form now, where the natural parameter vector will have this form here. And these functions here, these functionals here, B0 and B1, have this form here. The dependence on R is in the exponent for X here. So these integrals are intractable. Now, the way, so the integrals have this form here, the B functionals have this form here. It turns out that you can replace the highlighted red component here by a linear combination of scaled Gaussian cumulative distribution functions. So phi represents the standard Gaussian CDF. Has anyone seen this kind of integral before? A Gaussian CDF against a Gaussian measure? Turns out it has a closed form solution. Yeah, you can find this on Wikipedia, the integral of a Gaussian CDF against a Gaussian measure. You can find that on Wikipedia. So what I'm saying is this now has a closed form solution. But how do we get a good approximation from here to here? So
oh, so it is an approximation. It's not a...
yeah, it's an approximation. So the blue curve here represents this function up the top here. And this represents our Gaussian cumulative distribution function. And what we have to do is choose these parameters S and P, and as well as K, the number of parameters, such that this linear combination of Gaussian CDFs is as close as possible to the blue curve. So we're going to use the infinity norm to, what do you call it? The infinity norm where?
Norm?
The soup norm. We're going to use the soup norm to minimize this. So
The blue line never changes, right?
sorry?
Does the blue line ever change?
No, that's staying. Yeah, we don't want to affect that. We want to get as close to that as possible. So when you optimize P and S when K is 1, this is how close you get. This is what you get when K is 2. And we're optimizing P and S on the left, on the right there, so you can see what their values are. And by the time we use 3 Gaussian CDFs in that linear combination, by I, you can't see the difference between these two curves. So we'll just go overkill and we'll use 8 of them just to be safe, you know. The more and more you use, the more the closer and closer you get between the two functions.
And how are these numbers calculated?
That was an optimization thing. I actually didn't do that part, to be honest. But we were able to get that as close as possible based on just some optimization strategy. Yeah. And actually, no, I didn't do that. Sorry, this was done in Monahan and Stefanski. They used an optimization strategy to get that as close as possible. And these are the values for P and S that you get. And we've got some theorems that we're able to show that so even though these things are close enough, it doesn't necessarily mean the integrals are going to be close, but we've got some theorems in this paper that we wrote that showed that the integrals will also be close as well. Yep.
If we change the logistic linking function by the Gaussian activity linking function,
The probit.
probably, do
Yeah.
we have a closed form, or does that you no longer have the exponential? Yeah, by something.
Yeah, but when you use the probit, you get a different kind of intractability that pops up. I've tried this with the probit as well, and there are other kinds of intractabilities that pop up as well. Yeah. And I think also I think since the logistic link is the one that's most commonly used, probably is the one that that was basically the one I wanted to address first. Yeah, so these are the updates that we use. Obviously, we use our approximations for these functionals B0 and B1 to get us what we want. Sorry, it's about these approximations here and how the integrals are close. Nope. And here's just the message passing algorithm that we use for the Bayesian logistic regression model. So that part's not that exciting. We're able to determine our logistic likelihood specification. But now we have all the tools that we needed, for instance, if we want to extend this to semi-parametric logistic regression. So that's what the model looks like up the top there. Notice now that we have these fixed effects and these random effects like we had in the Gaussian semi-parametric regression problem. So we have our logistic likelihood fragment, which we just derived. We have our Gaussian penalization fragment, which we've gone over a couple of times now. We have these iterated inverse chi-squared fragments. We've seen them a few times, as well as these inverse chi-squared prior fragments, seen all them a few times as well. So in applying Bayesian logistic regression, we literally don't have to do any work, just copy and paste bits of code that we've already used. This is the general model, the general algorithm. And these are the kinds of fits that you can get when you run the variational inference algorithm to fitting non-linear probabilistic curves. So I guess now we can probably have a look at a bit of code. I don't think it will take too much time unless you guys want to try and put bits and pieces of the code together, but you're probably tired by now. But is there any way I can get the code, show the code on the screen?
Yeah, you can just go on the web
Browser, right?
and share that, yeah.
Sharing this.
Sharing, yeah.
Stop sharing?
Yeah,
Can we stop recording as well? Or you want to keep?
Yeah, probably. I'm just going to go through the code just to show what it looks like. I'm assuming people don't really want to start coding up right now. It's
Okay.
I mean, you're welcome to if you want to.
Good, sounds good.
Yeah, I just basically want to show what a script would look like for variational inference.
Do you have it on?
It's on the GitHub repository, which yes. So if we just go back to here. Maybe we just share. I'm gonna have to. Okay, yeah. I was hoping maybe to run a bit of code on this, but
Are installed on,
yeah, that's I just
I mean, it might be.
If you join the call from your laptop, you could show your.
yeah, I could probably
Yeah, that's brilliant. We can't record that, but yeah, well, maybe we can.
Yes. Just keep recording, it will record the screen.
Stop share. You have the link, yeah?
Sorry.
You have the link.
Actually, yes, I do. Actually, yeah. So this will take me a couple of minutes just to get set up.
Maybe Felipe, you can just pause the recording for now.
Okay.
Should I do it from up there?
No, you can.
Me from here?
There it's.
Okay, great.
Very vague ideas.
There's an asymmetry within player in the questions.
Apparently wasn't
You want to be able to.
super difficult. Usually TMC works with proposals, so you need to propose how to split the clusters.
Structurally, it's like asymmetric, but it's
Very tricky.
gaming.
And that.
We won't get around to that in this piece again. Oh, yeah. Yeah, I think very sluggish.
Because it's the mathematics has there is
But it's fun.
Okay, guys. So this is this is just some data that was generated for like that semi-parametric logistic regression. This is the nonlinear curve that you saw on the board before, and up here you have like the ones and zeros for where the data was generated. And I think there are 1,000 data points. Yeah, so n's 1,000. We're going to do 100 BMP iterations. We're going to use 15 plus 2, so 17 spline functions. And this is the form of the nonlinear curve that you saw in blue. So this thing here.
Hardcore, okay.
Yeah. And so that's what this thing here is. And that's all you need to know, really. You've got your vector of matrix of fixed effects, your X, your matrix of spline functions. Is that a bit better?
Yeah.
Yep. Yeah, and that's basically the data generation process. We have a high parameter specification, so your variance on the fixed effects, which is this guy here, and a parameter A, which is just your it's the hyperparameter that you set for your inverse chi-square prior distributions. The higher this value is, the more uniform that prior will be over your standard deviation parameters. And here's eta represents our vector of natural parameter vectors. Don't worry about what G is. That's to do with the graphical parameter for the inverse Wishart distribution. I don't want to get into that today. But here's your eta vector with all the messages that are going to be passed. So you have a message from B to U to the likelihood specification back to B to U, and so on and so forth. We then initialize all of those messages, and then we step into the loop. And here's where so for instance, B to U, the message it passes on to the likelihood specification is just the message that it received from the penalization specification. Like that's just that natural, the natural passing on of messages that's going on there. Then when we want to update the likelihood, we just use this function here, which captures all the messages that are required in that likelihood. So this logistic likelihood fragment, I use it in this semi-parametric regression model. I can also use it directly in a simple logistic regression model, and so on and so forth. And you have the same updates here for your penalization fragment and your iterated inverse chi-squared fragment. That's what this function represents. So that's really all there is to it. Every time you want to add an extra layer to the model, you just have to include the name in the natural parameter vector and copy and paste some existing code into this if you have to extend it. So we run through the fits and we get the following fits to following variational inferences on the curve.
Which is slightly different from the one that I think was showing on your slides. Did you use a different?
I don't think I've set the seed. So I haven't. So yeah, I haven't set a seed or anything like that. So you're going to get a different fit every time. Yeah. That's basically the body of what my work looks like now for variational inference. I never code things up directly by determining parameter estimates and all that stuff. I directly just copy and paste. So for instance, when I saw that I needed a logistic likelihood fragment, I just, copied this from the simpler model and put it directly into this problem here. When I say by the simpler model, I'm talking about this logistic regression model here. So here, this is the curve that was used to fit the data. This is a linear one now. It looks like a curve because you've got a straight line that you've had to turn into a probability structure. And in this one here, you'll notice that this fragmented, this code here is identical to what we have. So I've used this logistic like frag here. That's also being used in this one here. So just copy and pasting things here at this point. Saved me a lot of time, means I don't have to do that much work anymore. Likewise, you can run through the inference. That wasn't great. Our estimates on the true the black line represents what the true coefficient is. Okay, so that one was a bit off. That one's better. And you can see our estimates on
each iteration. Okay.
After 100 iterations. Okay. Yeah. Sorry, I should actually explain that a bit clearer. So it's our estimate on the probability curve. Remember, it's a linear problem, so it's beta naught plus beta 1x, and then you pass it through the logistic link. And here are our inferences on beta naught. So that's your posterior, the red's your posterior for beta naught, and the black line is the true parameter, and this for beta 1.
And this is after 100 iterations.
100 iterations, yeah. You could probably do, I haven't enforced any convergence criteria here. I've just go for 100 and yeah. But in principle, you would monitor the elbow as you go. Yeah. That's basically message passing in a nutshell. Like the idea is just to make your work modularized, so you don't have to keep so that you can take advantage of simpler stuff you've done with previous models before.
So do you guys plan to make a package and you put small fragments so that other users can use it?
Yeah. Sorry, you saying like as in like online, like a library, like. Yeah.
Library, something like that.
Yeah, that would be the end goal. I think that'd be more something for Matt Wan to do, because he's got postdocs who work under him and I don't. So, I think that would be the end goal for this, to have a library such that it can handle those kinds of just direct computational implementations.
Yeah, I mean, even if just the fragments that you have, because you have many situations that you try to reuse the same thing with the fragment, you kind of components of models that other users can just take from that and plug into the model.
Yeah. So for instance, like for myself, just for myself here, and actually you guys have it now if you've downloaded it. I've got these functions here listed in like a little library for myself. So I just store them in there whenever I find a new fragment, I derive it, code it up in there, and then just reuse it whenever I have to. Yeah.
Quick question.
Yeah.
When is this worth using and when is it not? Like, what are the scale of the problems where you would want to use message passing versus like Monte Carlo or other methods?
Like in terms of N and P, or in terms of N and P, like a number of data points, a number of parameters, and the sort of.
Oh,
thing,
just
or
like
generally.
just generally, like, is there like, because there's data dimensionality, but then there's also like complexity of the problem. Like, maybe a one-dimensional problem that's very complicated.
Yeah.
So the variational family itself, like if that is not matching the target sufficiently, then you can have potential issues as well. So how do you know which problems are worth like using this versus the ones that are?
So far for the models I've addressed, so the kinds of things I've worked on the most, logistic regression. So like when conjugacy doesn't follow, streamlined linear mixed models, and functional data analysis. I found for those three things that variational inferences has been quite strong. When I was talking about the streamlined versions for the linear mixed models, the derivations that we made can't actually be used in MCMC formulations, or at least in the Gibbs sampling approaches, we can't use them there. So for the models I've looked at, variational inference has been very handy. I can't say that's the case for every model out there, but for the models I've looked at, logistic regression, semi-parametric regression, linear mixed models, and functional data analysis, I found variational inference has been very handy.
Even for those problems, like, is there any feedback to know when you are doing good or bad?
Oh, that's a good point. So you're asking, like, how do I know that this is actually
Because it
good?
will converge, it'll give me something,
But how do I know?
Yeah, I don't know.
I get your question. Yeah. To be honest, I actually always compare it against MCMC, just to be safe. As long as the results I get are comparable to MCMC estimates, and when I say comparable, they have to be very close. Then those are the kinds of and that's what I found with the logistic regression. So those posterior density functions I just showed you for the logistic regression problem there, when we actually went into deep work on that and published the paper, we actually had very nice coverage with the MCMC estimates. So that when we're actually developing them, we actually do go through MCMC as well, just to have another model to compare against. Yeah.
It's possible to relax it.
But then the whole purpose is lost, isn't it? Because I mean, what you're coming up with this is because you don't want to do MCMC because it's faster. So if you have to do MCMC to check that this one is doing the right thing, I mean, obviously there is going to be enough experience at one point to understand when you don't need to do the MCMC analog. Do you get my point?
Yeah, there are times where I've looked at problems and I've had enough experience to say, okay, this should be strong enough to handle itself on its own merits. But that's usually based on previous work that I've done where I've set up and established a model and then compared it with an MCMC version just to make sure that those comparisons hold. But I would say once the model's set up, then when you're applying this stuff, you can go straight to the variational inference approach rather than comparing it with an MCMC alternative.
Okay, thanks.
Yeah, stupid question, but this is essentially just another way. So if you were to run message passing or the mean field variational inference, it would be exactly the same thing.
Yes, you would get the exact same, because it's the same optimization. In both cases, you're minimizing the Kullback-Leibler divergence based on some kind of posterior density function factorization.
Okay,
Yeah. You assume independence of certain parameters, so they're both doing the exact same thing. And I think we were just having a talk just previously, yeah. So this is the exact same. The computations are exactly the same as standard variational inference. You're just doing things in a more modularized approach.
and the theoretical guarantees are exactly the same.
Yes.
I mean, very
Yeah, that's why I didn't bother going over any theory, because all of that stuff carries over. But I guess the point, the take home message for me here is that it's not so much about all these accuracy things here. You can get these exact same results doing the standard approach. It's just that if variational inference can be a serious alternative to MCMC, I really do think you need these modularized versions, because you'd spend just as much time trying to derive these things, then code them up. So taking that amount of time into account, it doesn't necessarily save you time in comparison to doing it with MCMC. And so that's why I sort of advocate for this message passing approach. And a couple of people have just talked about, the necessity for a library on this. I agree. It would be good if we could get like a nice library for this kind of work.
Has there been any, because right now we're assuming we have our variational family comes from like a mean field approximately. Correct?
Yes.
What if you allow for more, does this framework adapt to more flexible families?
So I've seen it used in expectation propagation as well, where I think I haven't done any work in expectation propagation, but you can actually use it in other kinds of optimization strategies. To be honest, though, every optimization strategy that I've seen use the Kohlbeck-Leibler divergence.
I meant less in terms of the optimization strategy, but more the actual, instead of a mean field approximation, like if I have another flexible family of variational references, is there ways of expanding to that? So instead of just like a mean field, but I also maybe add like more complex mean.
Could you give me an example? I'm not really following
So
that.
for example, if I have, say, parameter theta1 and theta2, I can say put factorize as f of, or say theta1 to theta n.
Yep.
So I can put, that's a very complex probability distribution. So I can make the mean field approximation. So I have f of theta1, f of theta2, et cetera.
Yeah.
But I can also maybe add f of theta1 and f of theta2. And pairwise.
Yeah, that's what we've done in some of this stuff here. When you have the fixed effects and the random effects, we don't assume that they're independent. We put them together. We're as selective as possible. We try to be as selective as possible when we put these independent structures in there. Usually, it's to try and separate regression parameters from variance parameters, because those are very difficult. The intractability there would be too difficult to work with. You can use whichever mean field assumptions suit you, and these fragments would follow into that into those kinds of specifications as well. But there's certainly no restrictions on the kinds of specifications that you would like, but you don't want to be too liberal with it to the point that you're completely letting go of any sort of accuracy or any sort of smart inference for your modeling.
I'm planning to go through the code now.
Sorry.
I'm planning to go through the code now. If we're done with the discussion,
Yeah.
stop the recording. Yeah, that's good.